Hello, welcome to another lesson of Unit 141. We keep on working for assignment 4 with tasks P11, P12. Today's lesson is about the photoelectric effect. Now, the first thing I want to ask you is, can you explain what's happening here? Got here this clip. There's a sort of a bulb with no air inside, and it's got these veins painted black on one side, white in the other, and what happens is when it comes out to light, it starts spinning, and when it's put on the shade, back in the shade, it stops spinning. So there you go, shade doesn't spin, light it spins. Can you explain this? So I'll give you a few moments. Please pause this video and come back when you've got an answer. I'll go to it straight away. Okay, so essentially what happens is this is light will be absorbed by the black side of the vein. It will be reflected by the white side of the vein, and that leads to actually an imbalance in force being applied on both sides of the veins, and that's why it starts spinning. So the effect is light. Light is um, impinging on the veins, on both sides of the veins, but it will push more the white side of the vein because actually it's photons, they will be bouncing back. So we'll see this has got to do with the fact that photons, they act as particles. We've seen that, but now we go even a little bit further. They can even have moment, like a particle that bumps into another particle and sets that other particle in motion. So we saw this in Unit 5, collisions. So actually, that is very the particle nature of light is put in in so it's evidenced by the photoelectric effect. That's what we're going to talk about today specifically. That's one of the things you need to talk about in task P12. So it's explaining the photoelectric effect. Let's see what that is. When does it occur? And it's quite a complex thing. So we're going to look at all the angles. Also, why is it that the photoelectric effect cannot be justified by just plain wave theory? It was one of the very first examples in modern physics that was not explained by wave theory, so involving light, but that wave theory could not account for. Now, we saw so that photons are the particles associated with the particle behavior of light, and now we actually take that even further. They can even carry momentum. That mean they can collide as a particle, and even more than that, it's they will interact with other physical entities like electrons or atoms as an individual entity, not as a collective wave of many photons that keep on being added to or bumping into the atom or adding energy to an atom or an object. It's photon by photon that interaction occurs in. That's a very big difference. So let's see what is exactly the photoelectric effect. I'm going to explain the physical basis first, and I'm not really going to explain the historical way that normally the photoelectric effect is taught. Normally, people teach, these were the observations done, and they went against wave theory because of so, and the only explanation could only be if you had photons as particles. No, I'm going just to straight away tell you how does the photoelectric effect work, and then we're going to understand backwards why is it that it doesn't fit the wave theory. That's another thing that you also have to comment on P12 is why this photoelectric effect is not compatible with wave theory. So photoelectric effect is simply this, is the emission of electrons by material, usually it's a metal, when light hits it. So if you've got, let's say, laser with light hitting a metal, normally what happens is you get electrons being ejected off that metal. They are called photoelectrons because they were generated by by the light. Obviously, there are electrons which were already inside the metal. They were just set free by the light as it came in. Why? Because the light actually gives them energy. So the physical picture is really this: is you got one photon in the beam that finds a one single electron, hits that electron, and transfers all its energy to the electron. And this is a really important thing: is that the photon, when it does meet the electron, the photon will die, will disappear, and all the energy of the photon will be given to the electron in just one go. So the photon cannot give a little bit of its energy and keep on living. It's either uh, the whole or nothing. Either it gives all its energy away and dies, or simply doesn't give any energy away. So essentially, it's like this. Electrons are inside the material. They are bound to the material. That means there's an energy cost to remove them from the material. That energy cost has got a name. It's called the work function. It's the minimum energy that one needs to spend to remove the electron from the metal or from the material. Obviously, different metals, different materials will have different work functions, and it's something that you can be measured and that we can find in tables. Now, as the photon comes in, it does bring an energy with it. It depends on the frequency. We already know that's Planck-Einstein relation. It depends on the frequency of the photon, carries a certain amount of energy with it, and it finds the electron. If that energy carried by the photon is enough to remove the electron from the material, that means it's at least equal to the work function of the electron. What happens is the photon gives all that energy to the electron and simply dies. And from that on, what happens is you've got an electron with enough energy to escape the material. And that's what's going to happen. It escapes the metal. Now, the kinetic energy, we can actually calculate the extra or the surplus energy between the energy given to the electron, that's the photon energy, and the energy necessary to remove the electron from the material, necessary to remove the electron. So this surplus to remove electron, this surplus is it shows up as kinetic energy. So um, you spend some energy just to take the electron away. Anything um, that is in surplus of that will show up as kinetic energy of the electron. Normally, this equation's got the word maximum attached to it. It's just because on its way, the electron. So as soon as it is released from the place it was, it does have this kinetic energy, but along the way it may lose because it's going to bump against other atoms and other electrons. It may lose a little bit of its energy. So it may turn out that some of the electrons we see outside will have an energy slightly lower than this one here. But we will still see a few of those electrons with this maximum energy. Now, a few things that we need to notice. Normally, in a normal lesson, I would ask you to play a little bit with this with a simulation tool. If you do have a computer, you can play a little bit with this simulation tool. But the observation actually that we can do from this tool are as following: is that no matter how intense the beam of light is, so no matter how many photons you've got here hitting the material, electrons will only be emitted if light has got a minimum frequency. So below that frequency, no matter how many photons you've got hitting the metal, there'll be no electrons coming out. So there's a threshold frequency, and that it's easy to understand. It's just this condition that the energy of the photon has to match the work function at least. Otherwise, the electron will not have, when it absorbs the energy from the photon, will simply not have a full energy to leave the metal. Also, another observation that comes from experiment is that the threshold, this threshold frequency, varies from material to material. Well, that's because the work function is different. A third observation from the from experiment is that as long as there's emission, so frequency is enough to have electrons being emitted from the metal, the energy of the electrons is proportional to the light's frequency. So we increase the frequency of the light, and we don't really see more electrons. What we see is electrons with higher energy. Again, that can be understood. Can be understood easily from this equation. More frequency, more kinetic energy of the electrons. Finally, the fourth and last observation we can do is that if light does have a minimum frequency threshold to emit to allow uh, electrons from being emitted from the metal, is the larger the number of electrons, or should I say, the number of electrons will be proportional to the light intensity. So more light means more electrons. This essentially has got to do with this: is more photons will release more electrons, and this is the final proof that interaction of photons is 1 to 1. Is one photon interacts with one electron to give it all its energy. So more photons will lead to more electrons. Okay, so I hope you've understood this because you have to explain a few of these things in task B12. As a preparation, I'll ask you to answer questions 1 and 2 from the worksheet. You've got also 2 questions in the stretch and challenge section. They focus the photoelectric effect and its explanation.